And it is my pleasure to announce our speaker today, Professor Oleg Zaboronski from Warwick University, with the talk Classification of Entrance Laws for Annihilating and Coalescing Brownian Motions. Please, Oleg.
Thank you very much. Let me try. Sharing my screen. Okay, it looks like I don't have a sharing permission.
Katerina, can you give the permission of sharing screen?
Try now.
Okay.
Perfect. Thank you. Okay, let me see. Application windows. This. Great. Okay. Good.
Okay. Now we will see your slides.
Can you see the slides?
Yes, now it is okay.
Perfect. Thank you. Okay, there we go. So I would like to discuss entrance laws for coalescing and annihilating Brownian motions on R. And this is a joint recent work with Roger Tribe, also from Warwick. Okay, so here's the plan. I will discuss a family of models for coalescence and annihilation. Then I will define what I mean by an entrance law. I will review the Python structures for the class of models I introduced, and then I will show how to use the Python structures to find all extreme points of the set of entrance laws. Okay, so I already noticed that this is a very friendly and informal seminar, so please stop me at any time, ask questions, and I will do my best to answer them. Okay, so this is what I'm going to do. I hope red trajectories on blue are visible. I start independent Brownian motions from either deterministic or Poisson lambda positions on the real line. And I will wait until the first hitting time. Almost surely it will be a pair of particles. And then I will flip a coin, and with probability theta, I will annihilate these particles. I will remove them both from the system, or I will coalesce them with probability 1 minus theta, meaning that I merge two particles into one, and then I will restart. So there is no problem building this model exactly as discussed when I have finitely many initial particles. Some care has to be exercised when you are dealing with an infinite system, but it can be done. So, and one of the motivations for this mixed systems is the description of the dynamic of domain walls for a Potts model. So, and the number of states in this model is related to theta by this formula. In particular, if particles always annihilate, theta is 1, then we get a two-state Potts model, which is the Ising model. And it's known that in the one-dimensional Ising model, domain walls annihilate. And if theta is equal to 0, which corresponds to pure coalescence, then Q is equal to infinity. So imagine that you have a Potts model with a large number of colors, then the probability of two domain walls annihilating is 0. Okay, so, and one model which you know better than I do is the Aratia flow. This is the model when theta is equal to 0, particles only coalesce, and I can realize it by starting with a Poisson initial condition and taking its intensity to infinity. So the so-called maximal entrance law. So, and here I tried to illustrate the Aratia flow. So the time is running horizontally, space vertically. So if you are sitting reasonably far away from your computers, it will appear that particles indeed start from every point of R, and then, but at any positive time, the density of particles is already finite, and you see the coalescence trajectories, the particle density decays with time as 1 over the square root of time. Okay, so here, so this is the family of models I'm going to discuss, labeled by this annihilation probability theta. Okay, so now I would like to discuss the entrance laws. So let me think of my process in terms of particle positions. So and xt will be the corresponding random variable with values in locally finite simple measures, counting measures on R. So it takes values in, and I will refer to this space as M naught. This process is known to be Feller. I will denote by T capital the corresponding semigroup. And the family of laws, which are the probability measures on M naught, will be denoted by Q, and individual members of this family by Qt. Okay, so I hope these notations are reasonably standard. The central notion for me is the entrance law. So the entrance law is a family of laws Qt on M naught, which satisfy this. You can think of it as a standard Kolmogorov equation. So I can either push my observable with the semigroup by time t, and then average over the law at time s, or I can average over the law at time s plus t. Right? So, of course, what is so special about this definition? It looks like a completely standard version of the Kolmogorov equation. Qs is equal to t star qs plus t. Sorry, qs plus t is equal to t star t applied to qs. But the point is that these integrals don't have to make sense when t and s are equal to 0. Okay, so and the example to keep in mind is exactly the maximal entrance law. So we start from every point of the real line, so there is no corresponding initial condition, but at every positive time, we already have a process taking values in M naught. Okay, so that's the object I'm going to study, and I already said that a typical example to keep in mind is the Aratia flow. Okay, so now if we switch from coalescence to annihilation, then things become quite a bit more interesting. Okay, so let me try to motivate what I'm going to do. So now my particles annihilate. So here you can also see trajectories of particles, but whenever they meet, the colliding pair is removed from our space. And to start with, I start my particles from every point of the lattice Z scaled by this number epsilon plus epsilon squared over 2, where epsilon is a positive constant. Okay, so in other words, particles are equidistant and they're separated by something close to epsilon over 2 when epsilon is small. Okay, so, and on the second graph, I am also running an annihilating system. But now I am starting particles in close pairs. First, I seed the points of epsilon z with particles. So I have particles at separation epsilon z. Then I seed particles at epsilon z shifted by epsilon squared. So in other words, now I have particles, pairs of particles separated by epsilon squared, and the distance separation between the pairs is epsilon. So, and I chose my initial conditions in such a way that the initial densities of particles coincide. And yet it is quite clear that what will happen for the second case is that pairs of particles will annihilate with a large probability. And you will have very few particles left at positive time. So you can see that I actually had to try the simulation several times to create at least 2 pairs which are visible on this graph. So, and it is quite clear that if I start taking epsilon to 0, in the limit, I will have no particles at positive times for these close pairs. And it's actually easy to check that I will get in the situation on the left, I will get a process whose one-dimensional distributions can be obtained from the Aratia flow by thinning with parameter 1/2. Okay, so now an interesting observation is that despite this difference, dramatic difference in the evolution for the annihilating case, if I consider coalescence, then in each case I will get the maximal entrance flow. So it will be true, for instance, in the situation described on the right, that very close pairs, infinitesimally close pairs of Brownian motions will immediately coalesce, and then you will end up with the evolution starting from density equal to half the density of what you would get on the left-hand side. But in the limit when epsilon is going to zero, this density diverges anyway, so there won't be any difference. Okay, so what did I do so far? So I introduced, let me see. I introduced my family of coalescing annihilating models. I defined what I mean by the entrance laws, and I tried illustrating that at least for the case of pure annihilation, it is quite important how you take density to infinity to get something like the maximal entrance law. Yeah, sorry. I already forgot where my sentence started, but I hope this picture demonstrates the difference. So are there any questions? Okay,
Alec,
wonderful.
could you please recall us,
Yes.
what is the topology on this space M0, M0?
Okay, so it's I'm using the topology of wave convergence.
But you see, when the particles are closer and closer, this conversion, the sequence is divergent. Is it correct? I mean, assume that you have just two particles and the distance between them is epsilon, and you send epsilon to zero.
Right, yes.
So the corresponding measure do not converge to...
Yeah. Oh, the paths are not continuous. In this topology, the paths are not going to be continuous. But imagine that you are taking particles closer and closer, right? So let's just calculate the result against a couple of let us calculate.
No, I mean the state space, your state space. So topology in your state space.
So
because in some sense you have a Feller process, but
sorry. So you are talking about the whole. So you are talking about the whole. You are talking now about not the law at a fixed time, right? You are talking about the state space. So I have CADLog. I'm using Skorokhod topology on the space of CADLog paths.
And I have also another question about entrance law. If you know the entrance law, then can you start from zero somehow?
Yes, this will be a perfectly good entrance law, and you will get zero for xt, for instance. So you will get a zero measure for all positive times for this particular model.
So every entrance law, in some sense, is a process, corresponds to a process that starts from the point zero, from some locally finite finite measure, like the Lebesgue measure or some other measure.
Well, not necessarily. So that's why they're entrance laws. So they don't start necessarily with anything. Let's take the maximal entrance law, right? Which roughly corresponds to you starting at every point of space.
Yes.
So basically,
this is my question.
Yeah. So what we have. So the only requirement is to have a semi-group property for all positive times. So in other words, initially you are not in M naught, but for all positive times.
Yes, I understand this. But my question was, sometimes you start from the Lebesgue measure, or sometimes you may start from Gaussian measure. I don't know. So is it?
Yes.
Will there be some differences?
Well, to a degree. So so any initial condition is an example of entrance law. Okay. So in other words, if you start...
Yes, I understand this. Yes, but there are some other.
Definitely, yes, there is a reach. So that was, I suppose that was the point sorry, I think I was unclear. So the point of this picture is to show that there are plenty of different entrance laws. So that you can start with different interesting infinities and get interesting evolutions at positive times. Perhaps when I state the classification theorem, it will become a bit easier or more clearer.
Okay, thanks.
Okay. Sorry, Andrei. So maybe you should ask me again near the end of the talk, because I feel like I didn't answer your question. Okay, so now let me review the Pfaffian structures. And I'm going to describe xt, so my empirical measure, in terms of its endpoint intensities, which I will be denoting by rho t. Okay, and its defining property is that if I take the endpoint density and integrate it over the product space consisting of disjoint subintervals of R, then I will get the expectation of the product of the number of particles in the corresponding intervals. Okay. So, yes, and there is a misprint here. This should be a capital A. All right. So this is a standard way of describing point processes. If, for instance, I were to take coinciding intervals, then in the right-hand side, instead of a product moment, I would have ended up with a factorial moment. Okay, so then let me introduce a simplex in RM, so which corresponds to me ordering my particles somehow. And then there is the following statement. So let us start with the deterministic initial condition. And then our process, so it is at any time a Pfaffian. So, and that means that the corresponding intensity can be written as a Pfaffian of a certain 2 by 2, of a certain 2n by 2n skew symmetric matrix whose entries are built out of 2 by 2 blocks. And here is an explicit formula for these blocks. So here we see our theta parameter, which governs the strength of annihilation. And the 2 by 2 matrix is built out of derivatives of a single function of two variables on V2. And dx stands for the derivative with respect to x, and dxy stands for the second derivative with respect to xy. Okay. So you can, so this is the definition of this 2 by 2 block on the diagonal. Right. And K itself, so I will be referring to K boldface by as a kernel, and K typed as a scalar kernel. So K is a scalar function, and it is the unique bounded solution to the following parabolic PDE. So we just have the heat equation, the standard heat equation on the two-dimensional simplex. So with the initial condition equal to, with the boundary condition 1, and the initial condition given by minus theta to the power of the number of particles in the interval x, y. So I think it would have been better for me to write here mu rather than x naught, my initial condition. Okay, so it turns out that these mixed coalescing annihilating particles are Pfaffian point processes. So their laws, one-dimensional laws, are Pfaffian point processes for any deterministic initial conditions. So which means that it is possible to characterize the whole transition density for the process in terms of Pfaffians. Okay. So, and then let me sketch the proof of this theorem. It is quite straightforward. So let me construct the following function depending on two variables. So one variable takes values in our space of counting measures, and x lowercase takes values in the simplex. And what I'm going to do, I'm going to count the number of particles in n intervals with endpoints x1, x2, x3, x4, and so on, x to n minus 1, x to n. Okay. So, and sorry, I always end up with missing some misprints. So I don't, at this point, this is just a deterministic function. I didn't need to put the subscript t in the formula. Sorry about that. And then an explicit calculation allows one to do the following. Okay, so we take the generator of my Feller process, so particles annihilate with probability theta, coalesce with probability 1 minus theta, and act on the first argument of this function. Okay, so and then it turns out that this result will be the same if I apply the generator for an annihilating system, theta is equal to 1, started from 2n particles to the second argument. Okay, so let us think. So L2, so here I have a measure. The second argument is a point in the simplex, but I think the correspondence is quite clear. So in the second case, when I am dealing with finitely many particles, instead of thinking of a measure, I'm thinking about its support positions of particles. So it is easy to recalculate the action of the generator in this case. And it so happens that for this special function, the action of the generator for the infinite system on this function is modeled by the action of the annihilating system on the second argument. And this is true for all values of n as well. So I have a whole family of these functions of two variables. And Markov duality is extremely useful. Imagine that I wanted to write down the evolution equation for the expectation of this function when I keep x lowercase deterministic, and I'm choosing and I'm evaluating my function at the value of my process at time t in the second case. Oh, sorry, I just wanted to check my time. Okay, so well, the derivative of such an expectation is going to be the expectation of the generator applied to my function. Now I can flip the action of the generator on the second argument. It's deterministic. The generator L21 is a linear operator, so I can pull it out of the sign of the expectation. And if I go through this process, I will find that the expectations of my functions, phi n, which I am referring to as duality functions, satisfy the following infinite system of PDEs. So the time derivative of the expectation of phi n, so it's a function of time and x lowercase, is given by the 2n-dimensional Laplacian applied to this same expectation. This is true inside of the simplex. And then if I try merging 2 points, then I will see, so try merging, for instance, x3 and x4. So almost surely xt of an empty set is 0, and I will end up with the expectation of the same duality function, except for the I have to throw away the colliding coordinates from the expectation. Okay, so in other words, on the boundary of my simplex, I will have this boundary condition. So the expectation of phi n is expressed in terms of the expectation of phi n minus 1. So, and if I take time to 0, I will get an appropriate initial condition. So I'm assuming that I'm always assuming here that my initial condition is deterministic. Okay, so, and of course you see that you can probably see the generator of annihilating Brownian motions in this description. Look, when particles whose positions are marked as x lowercase are well separated, then my annihilating Brownian motions move independently, and their generator is exactly 1/2 of the 2n-dimensional Laplacian. If two of my particles, in this case xi plus 1, bumped into each other, they are immediately removed from the system, and I am getting the duality function of a lower order. Okay, so this is exactly this in this is exactly this discontinuity corresponding to annihilation. Okay, so and the initial condition, nothing is happening to the initial condition. Okay, so now this is an infinite system of PDEs, but it is unlike, say, the Bogolyubov chain, it is a nice infinite system. So if I know, so f0 is identically equal to 1, from this I can find f phi 1, the expectation of phi 1, because the initial condition involves the expectation of phi 0. And if I manage to find phi n minus 1, then I can use it as the boundary condition for the equation for the expectation of phi n, and I am done. It turns out that the unique solution, the unique bounded solution to this system is given by the Pfaffian of the matrix, which is built out of what I'm referring to as scalar kernels. Okay, and this formula is only true inside of the simplex. And here the another misprint. So the kernel itself is the expectation of phi 2, not phi n. And this is checked by inspection. So you check the equation, you check the boundary condition, you check the initial condition that it's all satisfied by Pfaffian, and then you ask an analyst and they tell you that the system has a unique solution. Okay, so and finally, now we are only getting the expectations of the duality functions. But of course, we now start taking the points. So we start taking the point x2 very close to x1, and the answer which we will get is 0. Sorry, is 1 unless there is a particle between x1 and x2, in which case the answer is equal to minus theta. And that means that by differentiating the expectations of phi n and merging points in pairs, x2 with x1, x4 with x3, we will be able to get densities. Okay, so that's the sketch of the proof. So what I've done here, I've stated the theorem concerning the Pfaffian structure of the process, and I sketched its proof. Let me check, are there any questions? So am I being too sketchy? Okay. All right, so now I would like to classify. So clearly, if you take a convex combination of entrance laws, it follows immediately from the definition that it's an extreme law. So now I would like to find all the extreme points of this convex set. Okay, so, and now I will pick. So notice that, let me, so this is quite important. In order to determine the law of the process for all, the laws of the process for all positive times, all I need to do is to solve this two-dimensional PDE. Okay, so everything is determined by the simple duality function calculated for a single interval and the solution to the corresponding heat equation in the simplex. So, and that is, so in other words, if you know, you can build everything from this simple elementary single interval duality functions. So which follows, for instance, from this formula. Everything is in terms of this two-point duality functions. So now let me solve the PDE for the single interval duality function with some initial condition f. Okay, so I will think about it more generally, and the corresponding solution, the kernel, will be marked by the superscript f. So if we're interested in deterministic initial conditions, so our f, as you've seen from the previous examples, is exactly minus theta to the number of particles, to the initial number of particles in a subinterval of R. Okay, so, and I will also mark by this superscript F the corresponding family of laws on M0. And of course, we know how to characterize QF at every fixed moment of time. We take the solution to our two-dimensional PDE. So, and out of it, by differentiating, building a 2x2 matrix, taking its Pfaffian, we can calculate all the intensities, and they completely characterize the law of a Pfaffian process. Okay, so, now I can formulate the classification theorem. So I would like to list all extreme points of the set of entrance laws. Okay, so, and it turns out that they are the entrance laws marked by some special functions f, given the initial conditions, which are a subset of L infinity functions on V2. And it's even, the answer is slightly different depending on whether theta is 1 or smaller than 1. So the set of classifying functions is just the product of measure when theta is equal to 1. So we're dealing with the set of then the products of functions, of measurable functions of one variable. So here x and y is in V2, and each individual f is a map from R to -1, 1. Okay, so so it starts reminding us of something. So when theta is equal to 1 in my example, then I'm dealing with functions which take only two values, +1 and -1, almost everywhere. But it turns out that if I want to consider entrance laws, then I should take all functions which take values in the interval from -1, take all products. Okay. Oh, by the way, it is clear that when theta is equal to -1, then this expression, so the number of particles between, say, points x and y, can be written as a product. -1 to the number of particles from 0 to x multiplied by -1 to the number of particles in the interval from 0 to y. Oh, good. So this product structure is reflected here, except for we know when considering all entrance laws, we no longer need to restrict ourselves to functions taking only values +/-1. We allow functions taking values in the interval from -1 to 1. And in particular, you can take a 0 function. So you will get 0 entrance law if you take the epsilon equal to 0 in the example I gave when you start annihilating particles in close pairs. Okay, so, and if theta is smaller than 1, then the functions which I need to use as the initial condition to calculate the scalar kernel are just are labeled by closed subsets of R. Okay, and the corresponding function will be the indicators that the intersection of this closed subset with my target interval xy is empty. Okay, so, and of course, you know that the famous duality corresponding to the Arrhenius law are exactly indicators of empty intervals. And it turns out that the introduction of theta doesn't really change that, even though the story is a bit more complicated. Okay. So, and the last remark is that it's a known-as description. If f is not equal to g, then the corresponding laws are going to be different. So, and for theta equal to 1, so for the pure annihilating case, perhaps the most interesting case, this theorem has been proven by these three authors in 2021, and they didn't use Pfaffians. They constructed a continuous counterpart of the Voter model, and they used Voter dualities and some information about the Voter model in order to prove the classification theorem. And unfortunately, the paper is quite long and technical. And I suppose the main takeaway from this talk is that if you are using the Pfaffian structure, all you have to do is to study solutions to a two-dimensional PDE in a simplex for all L infinity initial conditions with the values in this interval. So basically, we're talking about a ball in L infinity. Okay, so is the statement of the theorem clear? Okay, thank you. So let me give a very rough sketch of the proof. So if we have an initial condition, if we have a measure in M naught, so I will also restrict myself to analyzing the case when theta is equal to 1. So I'll give the reference where you can look at the full proof at the end of the talk. So, and okay, so here are our spin functions. The terminology comes from the Ising model. So we're looking at the parity of the total number of particles in the interval xy. So this is the duality function for theta equal to 1. And then it turns out that any function in C1, okay, can be, these functions are tensor products of factors which are just functions of one variables, taking values in the interval -1 to 1. So they can be all approximated by the spin functions in the weak star sense. Okay, so now for all values, for all values of n, if you start your process with the initial condition corresponding to mu n, it's a Pfaffian point process. And then employing the convergence, you can check that the limit is also Pfaffian, so that requires, again, some control on the derivatives, as well as certain employment of Pfaffian structure, but it's really it's a technical point. Due to the all I want to say that the proof that the limit is also Pfaffian is quite easy. You immediately get from this, right. So this is what we know, that QF is a Pfaffian point process. Then some general fact which has nothing to do with Pfaffians to start with is that any entrance law can be decomposed in terms of elements in terms of the laws, started from this particular initial condition. So started from this entrance laws QF. How you do that? Well, we just use the fact that Q is an entrance law by writing it by writing this decomposition, so which is true for all values of r smaller than t. And now the cool thing is that so we can use we can think of the action of the semigroup applied to F as our interacting particle system started from an initial condition mu. Of course, we didn't have an initial condition to start with, but now we're sort of starting at time r at the initial condition mu, and then we average over all initial conditions. Oh, good. So this can be, so now I know, okay, I actually lied. The Pfeiffian structure is quite crucial. So I know that the corresponding process is Pfeiffian, and it is Pfeiffian exactly with the spin function corresponding to F. Okay, and that allows me to write down the decomposition using the push forward measure. Okay, so and now you see that if I can take r equal to 0 in this formula, let's look at the first expression and the last expression. So I can find a null sequence Rn such that the corresponding sequence of push forward measures converges to something which I shall call theta. And then all of a sudden you get the formula giving you a convex decomposition of an arbitrary entrance law in terms of the entrance laws labeled by elements of C1. Okay, so and then the Pfeiffian structure is equally easy to use in order to prove the extremality of these entrance laws. So here by F I mean a function of a single variable. I'm using the fact that C1, the elements of C1 are tensor squares of functions of one variable. And I'm just assuming for a second that this law is not extreme. So then I can write it down as a convex combination of two other laws labeled by function g tensor g and say h tensor h. Okay, but then of course we know that we already checked that each of these laws is Pfeiffian, so we must have this relation. Okay, so imagine for a second that my functions f are not just measurable but continuous. Then I can evaluate this identity at the same point, and I will find that for almost all points in X, I will have, and all values of n, which is essential, I have to have this identity. Okay, so this is really becomes an identity between initial conditions. So the Pfeiffian structure allows you to say, oh, if my law is a convex combination of laws, then my initial conditions should be a convex combination of initial conditions. Of course, the unique solution to, you can only solve this identity if f, g, and h coincide up to a sign. Okay, so in step 4, we managed to decompose any entrance law in terms of entrance laws labeled by elements of C1, and in step 5, we check the extremality. So that's the sketch, modulo technical details, that's the sketch of the theorem, and I try to emphasize the role of the 5n structure. Okay, so are there any questions? Okay, good. So let me conclude. So I think the details can be a bit obscure, but the general idea is that if you have essentially if the transition density for your process is 5n, then you can always reuse the question of classifying the entrance laws to the analysis of a two-dimensional PDE. So I think the result, as stated, holds in a much greater generality. For instance, at the moment we're discussing a very interesting model with Andrei and Mykola. This model consists of coalescing Brownian motions, but with drift, or more generally coalescing ethos diffusions. And this model has some very non-trivial behavior for certain choices of the drift. And it has been worked on by Rogovtsov, Marchansky, Ryabov, Bell. I'm madly sorry if I missed any references. This field is relatively new for us. So you could also consider more complicated models. For instance, you can look at annihilating Brownian motions with pairwise immigration. So this would correspond to the kinetic easing model at positive temperature. And you can look at coalescing Brownian motions with branching, which can be obtained by sampling the Brownian net. And I think you can classify the entrance laws completely as well. So here's the reference. It's a relatively recent archive paper. So if you spot any misprints in this paper, I would be very grateful for your comments. And I can't resist pointing out that this paper is, sorry, that this paper is 8 pages long, and the original paper where theta equal to 1 case was considered it's about 50 pages long. So I think that's the saving due to the 5n structure. Okay, so, and this is it. I think I did manage to finish on time. Thank you for your attention.
Thank you very much for interesting talk. And maybe someone have comments or questions, please.
I'm not sure if this is a clever question, but there are also the terminal point processes. So is this somehow connected to what you're doing or not?
Yeah, I think this is an excellent question. So my belief is that let me take a concrete example. So let me look at Dyson-Brownian motions. So the main ingredients are still there. So you have, so it is determinantal for any deterministic initial conditions. Everything is determined by a kernel, which is a scalar function, in this case of 2 variables. And to be honest, I think that this would be an excellent project for a master's student, because people are very interested in the structure of determinantal point processes, and somebody could probably solve this problem for this case. Yeah, definitely.
Thanks.
Oh, thank you, Georgi.
Okay,
I
other
have
questions, please?
one small question about this duality. So was it obvious from the very beginning that you have such nice property, or not?
No, no, it wasn't at all. So it was known that the Markov dualities were known for the case when theta is equal to 1, the Ising model, and theta equal to 0, the coalescing model. We didn't have much hope in the general case, but we played a little bit, and this is what came out. This is very lucky. I would say that dualities, these rich sets of dualities, they models which allow for these rich sets of dualities, they are counterparts of quantum integrable models. So first of all, what do I mean by the rich set of dualities? So if I know the expectations of phi for all n's and all values of arguments, then I know the law for arbitrary initial conditions, for arbitrary deterministic initial conditions, and fixed time. So, and it turns out that for all the cases which are considered in are listed in the conclusion, except for the model with drift, the generators of these models, they lie in the so-called Hecke algebra. There are certain relations between the differential operators representing the generators of the model, so which mean that they have a very rich algebraic structure, and this algebraic structure can be seen responsible for these duality functions. But it's to have such a structure is very rare. It is I probably wasn't very clear relating to the integrable bonds, but it's like having complete integrability.
Yeah, thank you. Yeah, duality is very powerful, but when you try to find it yourself, very often it is impossible.
Exactly. You have to be very lucky. And to a degree, it is surprising that these classical models of interacting particles have these dualities. This probably suggests that they are by themselves labeling some universality classes of models, similarly to, say, KPZ universality class. And indeed, there is a connection between the 5 endpoint processes we're discussing here and 5 endpoint processes appearing in certain non-Hermitian random matrices. So you are definitely right, Andrei. So this is a very rare structure.
Okay, next question, please. I also have some questions. Firstly, about this duality too, because sometimes it helps to describe the initial process in terms of martingale problem. So, what do you think? Do we have such possibility here or not? Can it help with studying of the process?
Right. So this is exactly the question which Roger asked the other day. The answer is that we do not know. So, but it is certainly, it would be very interesting to try.
And also, I have to mention that for some kind of Markov measure-valued process, for example, as far as I remember, for super processes, even for original process, for initial super process, branching Brownian motions, the dual process is very simple, like it was very simple process. So,
yes, deterministic.
But sometime when we study such flows of interacting particles, we use term duality in other sense. There is dual flow. Yes, we can. So it is a very different thing. But do you think it is possible to have an analog of the net for this annihilation coalescing system?
All right, yes. So that's an excellent question. So again, I cannot answer it in full generality. So let me go back to the duality formula. Okay, so this is the statement of Markov duality. It is literally relation between two functions, right? However, for the case of, say, let me take the simplest case, the web. So there is a strong type of duality between the, so it is possible to couple two identical copies of a web in such a way that for you have forward paths of a web, backwards paths of the dual web, in such a way that these paths do not intersect. So this coupling is called strong duality. So because you can literally restore the paths of the dual web by looking at the paths of the forward web. And it turns out that when you have strong duality, it is often possible to derive Markov duality of this form. So that's the relation I know of. Of course, there is nothing as lucky in the opposite direction. At least I don't know a general coupling construction.
Okay, and the other questions is related to your description of the external points. You get the external points considering the two-dimensional parabolic problem with the very special set of initial conditions. Yeah, and this set of initial. So let me ask you the following question. Since you have such not usual for partial differential equation set of initial conditions, then maybe it is good to have some topology in the solution which will which allows to include such conditions, like some negative Sobolev space or something, in order then to say that your external points just came from well-known functional analysis theorem, yeah.
Right. Yes, that's right. Yes. So interesting. Yeah. So at the moment we use the weak star topology, and then we got compactness just by Ala-Glue theorem because our functions are inside of a weak star ball.
Yes, I understand.
Right, but your suggestion, I think, goes a bit deeper than that. So maybe there is a topology which will give us all our results much easier. In a much easier way. I don't know.
We can then use Crane-Millman, and that will be okay. And the last question is the following. You get the all in the flow as a convex combinations of the external points, external entrance law. But every this external point is corresponding to some system of coalescent particles with specular.
Yes.
What is corresponding? How to describe this convex combination? Can it be constructed in some probability sense? Of course, we can say. Let us take the mixture of the. It will be okay. But it is interesting to have some probabilistic
yes,
mechanism.
Absolutely, Andrei. I think this is modular details. This could be quite straightforward. So, for instance, all you need to do in this case is to put a probability measure on C1. So, and that will be your initial condition.
So, what we can say, how the particles are distributed in the S0?
All right. Yes. Good. So it will be so for if you fix F, right?
Yeah.
So then your one-dimensional distribution is a Pfaffian.
Yeah.
Right. And then if you now put a measure on Fs, so you will get all intensities as expectations of Pfaffians. So they also, they no longer have to be Pfaffians themselves, but this is an interesting extension of Pfaffian point processes when you can still write a formula for all intensities. Sometimes study them, yeah.
Okay, thank you very much again for interesting and informative talk. Hope to see you again and see you in Kiev personally.
Yes, I can come at any time. I am on sabbatical.
Okay, then deal. We will speak about it. Yeah. Okay. Okay. Good. And then the next for today we finish our work. Next speaker will be Mikhail Tretiakov from Nottingham. For today, that's all. Thanks everybody for your attention, and bye.
Thank you. Goodbye.
Thank you. Bye.
Goodbye.